Comes to students, in the last video we have learned about the open cover definition of compact sets and have also seen the Heine Borel theorem to match that definition with our intuitive definition of closed bounded sets are compact in case of real numbers. So before proceeding today, let me rectify a mistake done in the last video. In this example 3, this example 3, I had given the cover as n delta x, as x minus delta x to x plus delta x. Okay, but this one, and later claimed that this will not admit a finite subcover. Well, that was wrong. The open set if you choose delta equal to half at the point half, then the half neighborhood of half is the entire 0, 1. So that is a finite subcover, obviously. So the rectified version is this, that you choose if delta x is that delta x for which the delta x neighborhood of x is entirely inside 0, 1, then you consider the open sets as the half delta x neighborhood of x, that is x minus delta x by 2 till x plus delta x by 2. This open sets you choose, and in that case this open cover will not have any finite subcover for the set open interval 0, 1. Okay. So coming back to today's business, we will learn another proof of Heine Borel theorem. Okay, the main motivation for another proof is that this version is much easier to understand, the proof we are going to learn today, and also to showcase the importance of Heine Borel theorem, for which more than one proof exists. All right. Okay. So a word of truth is that this proof what we are going to learn today is more one-dimensional in nature. All right. So this cannot be used to prove Heine Borel theorem in higher dimension. Let me tell you that Heine Borel theorem is true for Rn as well. So the proof which we are going to learn today cannot be extended to a higher dimension, whereas the other proof we learned yesterday, the other day, can easily be extended into higher dimensions. Okay, so let us see the proof. Now we will have the proof today in two steps. First, we will see that closed subsets of a compact set are compact. This we'll see first. Closed subsets of a compact set are compact. Okay, and then we will see that the closed and bounded interval AB, since K is bounded, we have K is inside a closed and bounded interval AB, that is compact. So our main proof will be showing that the closed interval AB is compact, and hence by the theorem I said just now, since K is a closed subset of that compact set, closed interval AB will be compact again. So this will be our flow of the arguments. Okay, so let us see the theorem first. So this is the theorem. A closed subset of a compact set is compact. Let us see the proof. It goes this way. So let K be a compact set in R and F be a closed subset of K. Fine. Now to show F is compact, consider any open cover. So we need to produce a finite subcover for any open cover chosen for F. All right. So let G, script G, be an open cover of F. Fine. Now, since F is closed, the complement of F in R, that is R minus F, will be open. Right. Now consider the open cover script G along with R minus F. That means you take all these G lambdas, you take all these open sets G lambdas, which make your the cover script G, and the set complement of F. F complement is an open set. So you take this portion and R minus F. Okay. Now this one will be an open cover of entire R, because this script G, this part is covering F, and R minus F is covering everything else. R minus F is an open set, and this is covering everything else which is not in F. So these two together, the script G along with R minus F will be an open cover of entire R, right? So now since this is an open cover of R, this also covers the compact set in consideration K, right? K is a subset of R, obviously. So this open cover G, script G along with R minus F is an open cover of R. So this covers also K. Now what we know about K is compact. So this open cover must admit a finite subcover as well. Say we call it G dashed, G are lambda 1, G lambda 2 up to G lambda M, and possibly R minus F, right? Because this G, script G is an open cover of F. So we do not know whether that covers K or not. So we possibly need R minus F in our finite subcover to cover K, along with some finitely many elements from the script G, right? So this one will be an open cover of K. This one will be a finite subcover of the compact set K. Now, since F is a subset of K, this G dashed, script G dashed, will also cover F. There is no doubt. But in this script G dashed, this R minus F has nothing to do with the cover of F, because this is entirely outside of F. So since this one, if this one has to cover F, then only these portions, G lambda 1 to G lambda M, these portions needs to cover F entirely. There is no other way out. So R minus F does not cover any portion of F. Hence, F is covered by the rest of the portion, G lambda 1, G lambda 2 up to G lambda M. But this is a finite subcover of F from script G, right? So, hence any open cover of F admits a finite subcover. Therefore, F is compact. Alright, so this small powerful theorem tells us every closed subset of a compact set is compact. This theorem, now a few remarks on this one. Now this theorem follows immediately from Heine Borel theorem. If we assume Heine Borel theorem, then this theorem follows almost immediately, because Heine Borel theorem says a closed and bounded subset of R is compact. So a closed subset of a compact set will be bounded again. So therefore, this closed subset will be a closed and bounded subset, and hence it will be compact. But since we want to travel the other way around, that we want to use this one to prove Heine Borel theorem, we are seeing a new proof of this one, fresh proof of this one. Also, this theorem, this result is true when Heine Borel theorem is not true. There are general topological spaces where Heine Borel theorem is not true, but there also this theorem is true. This theorem is almost universally true whenever we talk about compact sets. So that is why this demands a new proof, this demands a fresh proof, and this proof is also a sort of universal proof to this theorem. Fine. So when we have this result on our hand, let us see the proof of Heine Borel theorem. So this is Heine Borel theorem, a closed and bounded subset of R is compact. That is, every open cover of a closed and bounded subset of R must admit a finite subcover. So here we are going to do the second proof of this theorem using this theorem. A closed and bounded subset of a compact set is compact. Fine? Alright. So the proof starts this way. So let K be a closed and bounded subset of real numbers. Now, then for some real numbers A and B, K must be within the closed interval AB, since it is bounded. We will show that this closed interval AB is compact. Then, Applying the previous theorem, as K is a closed subset of the compact set closed interval AB, we can say that K is compact, right? So now, while proving this one, AB is compact, let G be an open cover of AB. So we want to furnish a finite subcover of script G from script G of AB. Fine. Alright. So we construct this set. The set is called S, and this contains all those elements from AB, closed interval AB, such that the closed interval from A to X is covered by finitely many open sets from G. Alright, pause a second, I'll repeat. S contains all those points from the closed interval AB, so that the closed interval starting from A to X is covered by finitely many open sets from G. So we are starting from A and we are looking at how far can we go along AB, along the line closed interval AB, so that we are still under finitely many open sets from G. Clear? Alright. Now, obviously, if we can show that this S, the set S is entirely AB, the closed interval AB, then we can say that the closed interval AB is entirely covered by finitely many open sets from G, and then that will prove this theorem, right? If we can show that S is entirely AB, then we, by the definition of S, the closed interval AB is covered by finitely many open sets from G, and hence we can say that the closed interval AB is compact, right? So our job is to show that this set S is entirely closed interval AB. Fine? Alright. So here we go. Now clearly the point A belongs to S, right? The point A belongs to S because the closed interval A to A, because the closed interval A to A is the singleton point A only, right? So then to cover a singleton point, we only need one open set from script G, right? So the point A is definitely there inside S, because the closed interval A to A is definitely covered by finitely many open sets from G. Also, S is bounded above by B, right? Because definitely the points are coming from the closed interval AB, so it cannot go beyond B, right? So A is a point in S and S is bounded above by B. What does this imply? This implies S is a non-empty bounded above subset of R, and hence we have completeness axiom on our pedestal. So by completeness axiom, supremum of S exists, right? Call supremum of S as small s. Now, of course, this A will be smaller than or equal to B, right? So now we claim that number one, S is small s is an element in capital S, and secondly, S small s is equal to B, right? We claim that small s belongs to S. That means S is the supremum, so we do not have any guarantee by default. I mean, we do not have any default guarantee that supremum belongs to the set. So we claim in this case that is not the case. The supremum will belong to the set, and belongs to the set means A to S is covered by finitely many elements from G, finitely many open sets from G, and secondly, S will be equal to B. That means the entirely AB is covered by finitely many open sets from G. So these are my claims. So let us see the proof of these claims. Assume for the first one, so the first one is small s belongs to capital S. For the first one, assume that it is not the case. Small s doesn't belong to capital S. Then S will be a limit point of S. Then small s will be a limit point of S. We have seen this exercise before, that if the supremum of a set does not belong to that set, then that supremum becomes a limit point. We have seen this exercise before, so we are using that one. So then S becomes a limit point of capital S. Now since the script G is an open cover of AB, since script G is an open cover of the entire interval AB, S belongs to sum of the open set G alpha from G, right? S belongs to S definitely belongs to the closed interval AB. We are looking at whether S belongs to capital S or not. So since S is a point in closed interval AB, S must be covered by some open set G alpha from the collection script G. Now, since G alpha is open and S is a point there, it is an interior point, so that means there is a delta positive such that the delta neighborhood of S is inside the open set G alpha as well. Now again, as S is a limit point of capital S, for this particular delta, there will exist a point x delta from capital S such that S minus delta will be smaller than x delta will be smaller than S. Remember, S does not belong to capital S, so this x delta cannot be less than cannot be equal to S. So we have this strict inequality, S minus delta less than x delta less than S, right? So, but as x delta is coming from S, the closed interval A to x delta, the closed interval A to x delta is covered by finitely many open sets from G, right? Then what we see is the closed interval A to S. Now definitely this is inside the interval A to S plus delta, closed at A, open at S plus delta, right? Because here we are starting at A, ending finishing at S, and here we are going till S plus delta. Obviously delta is positive, S plus delta is bigger than S. So this interval A to S is inside A to A plus delta. Now what is A to A plus delta? A to A plus delta is A to x delta and then S minus delta to S plus delta. Remember, x delta is to the right of S minus delta. So A to x delta is there and S minus delta goes somewhere over here. If somewhere in between A to x minus delta. So A to x minus delta and then S minus delta to S plus delta, this will totally cover A to S plus delta. I urge you to draw a picture over here to convince yourself. Okay, this is extremely easy to see. This will be true. That A to x plus delta, the closed interval union S the delta neighborhood of S is this interval A to S plus delta. Fine. Now something to note here, that since x delta came from S, so A to x delta, this part is covered by finitely many open sets from G. So this part is covered by finitely many open sets from G. Now what about this part, the delta neighborhood of S? This part is covered in a single G alpha over here, right? So this part A to x delta is covered by finitely many open sets and this part is covered by only one open set. So that all together this is also covered by finitely many open sets from script G. So AS is covered by finitely many open sets from script G, right? And This is the definition to belong to capital S. So small s belongs to capital S. This is the proof of our first claim. So the second claim is we need to show S is equal to B. So assume that S is something strictly smaller than B. Okay. Let's see what contradiction we arrive at. Then, as in the last argument, we can always choose delta positive such that the delta neighborhood of S is in G alpha, just like over here, and S plus delta is still less than B. We have chosen S to be smaller than B, so that becomes A to be an interior point of the closed and bounded interval AB. So therefore, we can still increase S to some extent that S plus delta will still be smaller than B, right? So we choose this delta such that the delta neighborhood of S is entirely in G alpha, and also S plus delta is smaller than B, right? Now, for this delta, this argument holds, and this A to S plus delta, is covered by finitely many elements from script G, as we have seen here. So the closed interval A to S plus delta by 2, which is definitely inside this one, is also covered by finitely many elements from G, right? Okay, this entire thing is covered by finitely many elements from G. Hence, A to S plus delta by 2 is also covered by finitely many elements from G. Why we need to do this manipulation? Because in the definition of S, let me go back a little bit quickly. Yeah, in the definition of S, the criteria is A to a closed interval A to S must be covered by finitely many open sets from G. So there we had only A to S plus delta by 2, A to S plus delta, and S plus delta side was open. So that is why we could not say that S plus delta belongs to S. But let's come back once again quickly. Yes. So A to S plus delta by 2, this closed interval is also covered by finitely many elements from G, because A to S plus delta by 2, this closed interval is inside this interval A to S plus delta. Okay. But this shows that S plus delta by 2 belongs to S, because these right endpoints are only elements of S. So S plus delta by 2 belongs to S. Now, do you see a contradiction? This is a contradiction to the fact that small s is the supremum of S, right? So hence, S must be equal to B. Our assumption S less than B led us to this contradiction. Therefore, S must be equal to B, right? So therefore, the closed interval AB, entirely closed interval AB is equal to S, and hence the entire closed interval AB admits a finite subcover from the script G. Hence, that is compact. Now, and K being a closed subset of a compact set is also compact, right? So this small proof is quite beautiful, and this is a much one-dimensional proof of Heine Borel theorem. In the next video, we will see the converse of Heine Borel theorem. Thank you for your patience. Bye.